Hey there, welcome back to Real Analysis. In the previous section, section 4.3, we got introduced to the very important fundamental notions of open and closed subsets of the real number line. These notions are fundamental in our study. We're going to be studying functions, limits of functions, derivatives, and so on, like from calculus. So the notion of open and closed sets play fundamental roles there. There's kind of a branch of mathematics in which one abstractly studies these ideas of open and closed sets in a space. We won't go into what we mean by that in detail in this lecture, but that branch of mathematics is called topology, and hence the name of the section here, the topology of the real number line. We're studying the open and closed sets of the real number line. So we're studying the topology of the real number line R. Okay. So our first theorem is going to describe kind of a general relationship that exists between open and closed sets. So I'll just kind of scroll up here and let you check it out. So what does it say? If you take a subset of the real numbers called A, so A is any subset of the real numbers, and then B is its complement. So the author is using that notation. I've defined it in the proof. I'll just talk about it right now. So by R/A, we mean those real numbers that are not an element of A. So it's the complement of A. Any real number either belongs to A or its complement. So those two sets union together to give the real numbers, and they're disjoint. No element is an element of A and its complement. So what the theorem is saying is that if you take this subset A of real numbers, then that set A is open if and only if its complement is closed. All right, so complements of open sets are closed, and not only that, any set that's closed is the complement of some open set. All right, so I'm going to just kind of launch into the proof. You might want to stop the video before I start and review, if necessary, those definitions of things like open set, closed set, interior point, and accumulation point, because I'm going to be heavily using those ideas in this proof. So I'm just going to kind of whip through it here in my usual video producing speed, but you can always stop and look up those definitions if you need to and make sure that you're kind of understanding the quantifiers and how I'm using those definitions to accomplish this stuff. All right, so you want to review open set, closed set, interior point, accumulation point. Okay, so it's an if and only if theorem. So let's start with one of the hypotheses. Let's suppose that A is an open set, and then I want to show B is closed. I want to show its complement is closed. So I want to show that every element of its, every one of the accumulation points of the complement is an element of the complement. So I start by picking an accumulation point of B, and I want to show that that's actually an element of B. If we can accomplish that, then we will have shown B is closed by definition. All right, so we're going to kind of proceed by contradiction, or you could rewrite this proof into kind of a contrapositive form here, but I'm just going to proceed like this. So I want to show that X is in B, so suppose it's not. Well, if it's not in B, then it's in A. And A is an open set, right? So every point in an open set is interior to it. So that means that there's some positive number epsilon, such that the epsilon neighborhood around my X is completely contained in the set A. It's because A is open, X is interior to it, right? But if that epsilon neighborhood is completely contained in A, then its intersection with A's complement is empty. Draw a Venn diagram. Stop the video and kind of draw a Venn diagram. If you take a subset of A, then it's completely contained in A, then that subset intersects A's complement in the empty set. All right. So if that neighborhood, we found an epsilon, so that the epsilon neighborhood of X is devoid of B. So in particular, it doesn't have infinitely many points of B, so that X can't be an accumulation point of B. Right? If X is an accumulation point of B, then every epsilon neighborhood of X is supposed to intersect B in infinitely many points. Well, this epsilon neighborhood doesn't intersect B at all. Okay, so the supposition that X isn't in B contradicts our assumption that X was an accumulation point of B. So X must be in B, and hence B is a closed set. Nice. All right. Stop the video and let that soak in. I'm just going to move to the second half of the proof. Now I want to assume B is closed and try to show you A is empty. To show A is empty, I want to show every point's interior to it. So let's suppose B is closed, and let's pick a point in A. I want to find an epsilon neighborhood that's completely contained in A, an epsilon neighborhood of that point. I want to show that this point X is interior. Okay, So if there doesn't exist such an epsilon, what would that mean? Well, then for every epsilon neighborhood of X is not a subset of A. All right. Well, that means that for every epsilon, I can always find a Y. If you like, you could say Y depends on epsilon, but I'm going to leave it out of the notation. I can always find a Y in that epsilon neighborhood, but it's not in A. I already said that X is in A. So then in particular, this Y that we found can't ever equal X. So Y is actually in the deleted neighborhood, right? Y is not in A, so it's in B. So if it's in the deleted neighborhood of X and it's in B, it's in their intersection, right? So, but what have I shown? I've shown for an arbitrary epsilon, I can always find an element in the deleted neighborhood intersect B. So that shows that this point X is an accumulation point of B by definition. Yeah, there's always some other point besides X in this epsilon neighborhood and in B. All right. So X was an accumulation point of B, but B is a closed set. So X has to belong to B. All right. But wait a minute, we wrote above that X belongs to A. Well, it can't belong to A and B because A and B are complements. All right. So once again, we've derived a contradiction. Okay. So there has to be some epsilon with an epsilon neighborhood in A. That is, X has to be an interior point of A. That is, A has to be an open set. Nice. Stop the video and see if you can't digest that argument. I'm going to just keep rolling here. The next theorem I want to look at is some kind of properties of open sets. These properties are fundamental in the sense that you want to be very familiar with them, know them well. Not all of them are new, but they're getting listed here just to kind of emphasize their importance, if nothing else. If you're interested in this abstract idea of topology, and then these properties of open sets actually become axioms when you talk about more abstract topologies on other sets, but we won't talk about that here in this course. Okay, so what are the properties of open sets? Well, first of all, let me kind of actually reveal the proof as I say these, because some of these things we've already proved. Last time we already showed that the empty set and the whole real number line are both open, right? So we proved that in section 4.3. I'm going to skip down to the bottom one. The complement of an open set is closed. That's what we just proved. We just proved it above in 4.16. I'm going to leave the third property as a homework exercise to you, an honest to goodness homework exercise. It's exercise 4.4.2, and that is that if you take the union of an arbitrary collection of open sets, it's always open. So an arbitrary collection in the sense of even over an uncountable index set, the union of any collection of open sets is always open. All right. Property 2, the one that I haven't mentioned so far, says that the intersection of a finite number of open sets is open. So not an arbitrary intersection, but a very strong restriction on it, only finitely many. So said more generally, that the intersection of any n open sets is open. So the proof of that should be done by induction on n. I'm just going to do the base case. I'm going to try to convince you that the intersection of 2 open sets is open. All right, and then I'll leave the details of an induction proof to you. So I scrolled fast there. You can stop and rewind. So let's take a couple of open sets. Let me call them A1 and A2. All right. I want to show that their intersection is open, so I want to show that any point in their intersection is interior. Maybe here I'm just going to say it out loud. If their intersection is empty, then that's an open set. So I might as well assume that their intersection is not empty. All right, so you can kind of amend that in the proof if you want here. After, yeah, I'll just kind of write it over here as a side. If A1 intersect A2 doesn't have any points in it, then it's empty. Or then it's open, excuse me. A1 intersect A2 is open. All right, so I might as well assume that I really can pick some X in their intersection. But still, I should be a little bit more careful than that. Okay, so let's just use the fact that A1 and A2 are open individually. If I pick X in A1, or if it's in the intersection, it's in A1. And since A1 is an open set, there has to be some neighborhood, I'm calling its radius epsilon 1, that's completely contained in A1. Every point in A1 is interior. But similarly, there's some epsilon neighborhood of X that's completely contained in A2. It's probably not the same epsilon. That's why I'm calling them epsilon 1 and 2. All right. Just take epsilon to be the smaller of those two numbers. They're both positive numbers, so their minimum is a positive number. And then if you take any point in the epsilon neighborhood of X, well, then its distance from X, the absolute value of Y minus X, is no more than epsilon because it's in the epsilon neighborhood, but epsilon is less than or equal to epsilon 1 because it's the minimum, right? But every point whose distance from X that's less than epsilon 1 is in A1. Similarly, that distance is no more than A2, so Y is in A2 as well. So any point in that epsilon neighborhood of X belongs to both A1 and A2. So the entire epsilon neighborhood belongs to A1 intersect A2. So X is an interior point of the intersection. X was arbitrary, so that shows that the intersection is open. Nice. While you're soaking that in here, I drew you a little colorful picture. It's just showing you kind of the construction and the proof. I've drawn A1 like it's the purple segment there in the real line. Of course, A1 doesn't have to be an interval, but I have to draw some picture. A2 is some other open set. I drew it like it's an interval, and then I'm indicating that I've got an X here in the intersection, so it's in the purple and the green intervals. And then I'm kind of trying to show you the epsilon neighborhoods. I'm not claiming these things are unique. I kind of drew them as big as they could. But yeah, epsilon 1 is the open interval around X that's contained in the purple interval. That looks about as big as it can be. So likewise, epsilon 2 is the open interval around X in the green interval. And in my picture here, certainly epsilon, which we said in the proof was the minimum of epsilon 1 and epsilon 2. Well, in my picture, that looks like epsilon 2. Yeah, so in the proof, we just said like, well, if you pick an element in the epsilon neighborhood of X, it's in both those sets. And sure enough, the picture says that looks consistent. Nice. I encourage you when you're reading this stuff, listening to these lectures, rewriting your notes from class, draw these pictures. They're certainly very helpful. They never provide a proof of anything, but they're certainly helpful. Everything we're talking about has kind of a geometric flavor to it, and it's more fun to imagine and draw pictures of the geometry. Okay, so let's move along here. I've got some properties of closed sets. These properties very much kind of correspond in some sense to the properties of open sets. I mean, after all, a set is open if and only if its complement is closed. So here, again, we've proved some of these things. I'm going to leave some to exercises, but let's just kind of rip them off in order this time. That the empty set and the whole line are closed. We proved that in section 4.3. Actually, I guess I'm changing my mind. I'm going to do them out of order. The complement of a closed set is open. That was from the opening theorem, 4.16. I'm going to leave property 3 as an exercise for you, that any intersection, notice that it's not a union this time, but any intersection of an arbitrary collection of closed sets is closed. Okay, and then the part I am going to prove here is that any union of a finite number of closed sets is closed. Okay, so these are sort of the corresponding properties for homework set for closed sets. You could argue these things directly. I could argue that this finite union of closed sets is closed by doing an accumulation point argument. But I wanted to take an opportunity and to remind you of something that you learned in your Math 240 set theory course called De Morgan's laws. This is not actually my favorite way to denote these complements, but this is the author. So this is taken from the end of your book in the appendix on some set theory. So what did De Morgan's laws say? I'll just highlight them as I say it. One thing De Morgan's law says is that the complement of a union is the intersection of the complements. So here I didn't quantify, but B1 and B2 here are subsets of this set A. So I'm looking at the complement of the union of B1 and B2, and it's the intersection of their complements. Likewise, the complement of an intersection is the union of the complements. So said another way, De Morgan's law says that complement kind of interchanges intersection and union, but you have to do it over the complements of the sets. It's actually true for any index. If you take any index collection of sets BI, the complement of the union is the intersection of the complements, and likewise, the complement of the intersection is the union of the complements. So I'm going to use De Morgan's laws to prove property 2. I want to prove that if you take any finite collection of closed sets, I'm calling them A1 to AN, I want to show their union is closed. Okay, so I'm going to use our opening theorem. One way to show that that union is closed is to show that its complement is open, right? That's what theorem 4.16 says, is that that complement is open if and only if the union is closed. But De Morgan's laws say that the complement of that union is the intersection of the complements, right? Each one of the AI is closed. A1 is closed, A2 is closed. So all those complements are complement AI. They're all open, again, by 4.16. The complement of a closed set is open. But by property 2, what you're going to prove, or the property that I proved above for 2 sets, and it follows from induction, the finite intersection of open sets is open. So the intersection of those complements is open, and therefore the union of the finite union of those sets is closed. Nice. Okay. Pause and soak that in. I hope that gives you kind of a template for how to do that homework problem, 4.4.2 or whatever it was. You can start 4.4.3. You can use the same technique. Try to use De Morgan's laws. All right. So I'm going to kind of end just teeing up a topic for next time. This is going to seem a little bit out of the hat, but I'll relate it to open sets here in a second. But this is just kind of an example. I'm calling it. I'm really making a definition, but we're going to talk about such ideas next time. And so this is sort of a good place to plant the seed in your brain. So if you give me some function from the real numbers to the real numbers, we're going to start talking about such things more and more as we move into topics of continuity, differentiation, integration, and so on. So I'm going to call, if you pick a number x in the domain, I'm going to say that that function is bounded at x. So that's the term I'm defining. It's underlined. If there's some numbers, epsilon and m, they depend on x. So that's why I'm writing epsilon sub x and m sub x. They're both positive. And then what they have to do is that the absolute value of f of z has to be less than or equal to m sub x for all z in the epsilon neighborhood of x. All right. So hopefully it kind of makes sense, this terminology. This function is bounded at x. I'm going to draw a little picture here as I speak. So maybe this is my number x. So this function is bounded at x if there's some epsilon neighborhood of x. I'm just going to kind of shade it in red. Yeah, so there's some radius that if you stay around that radius, then for inputs inside that epsilon neighborhood, maybe I'll write its name down here, n sub epsilon of x of x. For numbers inside there, there's this number m, also depends on x. And the function values stay below that dotted line in absolute value on that neighborhood. So if you're kind of thinking about the graph of the function, or the graph of the absolute value of the function rather, it has to stay below that line, right? So it's bounded at x in the sense that there's some neighborhood around x on which the function is bounded. Okay, so that's kind of the definition. Now I want to say something about what the nature of the set of points where a function is bounded. So the neighborhood, the epsilon neighborhood of x is certainly an open set. Yeah. So if you pick some element y in it, well, then there has to be some neighborhood around y that stays in there. My picture is going to get a little micro because I drew it kind of small, but I'm just saying if you pick a y inside that epsilon neighborhood, well, then you can find I called it delta neighborhood of y that stays in there, right? So in particular, the function is bounded by the same bound, m sub x, on that entire delta neighborhood. The delta neighborhood is a subset of the epsilon neighborhood, right? So f is also bounded at y. So saying it one more time, if you have a function bounded at x, then that function is bounded at y for all y in the epsilon neighborhood of x. Okay? So that means if we let, say, E be the set of points where f is bounded at them, E is the set of real numbers x where f is bounded at x, then E is the union of all those epsilon neighborhoods, right? One of these things, this is a pick a point proof. I'm going to kind of leave the details to you, but one of these inclusions is kind of by definition, right? If you pick some element of E, well, then by definition, because it's bounded at X, there's some epsilon neighborhood such that blah, blah, blah. X is certainly an element of the epsilon neighborhood at X, so it's an element of the union. No problem. My comment above is the other inclusion. If you pick something in this union, well, then it's in some epsilon neighborhood of X for some X in E, it's some Y, but we just said that Y is therefore also, F is also therefore bounded at Y. So Y is an element of this set E as well. So the set of points at which F is bounded is the union of a bunch of these epsilon neighborhoods. Each one of these epsilon neighborhoods is an open set. Arbitrary unions of open sets are open was one of our theorems in this section. So this set is open. The set of points at which a function is bounded at those points in the technical sense above is an open set. Cool. Okay. I'm going to end the video with just kind of one more definition, again, kind of teeing up for next time. I'll call a function on some subset E of R. So here, I didn't include it, but here E is a subset of the real numbers. F is just a function on E. Maybe E is all of R, maybe it's not. So I'm going to call that function locally bounded on E if it's bounded at X for every X in E. All right. So a function is locally bounded if it's bounded at every X in its domain. Okay, so that's where I'm going to stop it. Thanks for listening.